So, I have graded assignments here. We'll pick them up at the end of class. And the current assignment, problem set 2, is due today. So on the web now are all of the current lecture notes up to yesterday's or Monday's lecture, and all of the video are compressed and ready for viewing now. Thanks to Ben and Rob. And the next problem set is posted, and it's a 2-week assignment as well. But don't wait. Get started.
Yeah.
Yes.
I'd like to say something on the form for this week.
Uh-huh.
I think we all had problems to finish it in time. Well, it was very much, but I don't think I can say something against that. But we should have more time, because most of the things we needed for it, we did in class on Monday. And as the problem session is also on Monday, actually we did almost everything on the last 2 days, less than 2 days. I think it's better if we have more time for that.
All right, well, we'll try to beware of, there was 2 weeks to do that. What we did on Monday was the hyperfine structure. There was only, the last problem required you to know that. The rest of that was just angular momentum addition. And if you had gotten started and had questions about the first week, I certainly could have answered that. So there were 2 weeks in that assignment, and I think there was quite a bit that you could have gotten started in the first week. And no one came to the problem session last week. I was there. So I will be cognizant about trying to make sure that if it's a 2-week assignment that you can get started on that work in the first week. So you don't, I agree, if you tried to do it all in the last week or in the last few days, it would have been a challenge. This current assignment, you should be able to do it starting this afternoon. And you have 2 weeks. So I think it's a reasonable amount of work for the graduate course here. But we'll try to pay attention. And if we're finding that the assignment is, you don't have the material you need to get moving on it once the assignment started, then I will certainly be happy to give an extension. So I'll be aware of that and just let you know. Okay? All right. So let's see. We were talking about last time, looking at now an atom with more than one electron, in particular an atom with exactly 2 electrons. So the generic problem here involves some 2 electrons and a nucleus. And if we ignore any of the effects associated with magnetic effects and associated relativistic corrections, and we concentrate to lowest order on the electrostatic interactions, then this is our Hamiltonian. It's a very simple Hamiltonian associated with the attraction of the 2 electrons to the nucleus and the repulsion between the 2 electrons. So we can think about this as each term associated with the independent attraction of each electron independently to the nucleus is a hydrogenic-like Hamiltonian. And then we have the correlation effects having to do with the interactions between the electrons. So a coarse approximation that gets us started here is to look at the problem from the point of view of perturbation theory, whereby we treat this as a perturbation and think about this as our zeroth order Hamiltonian. And so our zeroth order wave functions then are the wave functions associated with two electrons, one in one of the orbitals associated with that hydrogenic atom and another with a potentially same or different orbital. So for example, the ground state here would be both atoms, or I'm sorry, both electrons in a 1s orbital. And in this case, we're thinking about that 1s orbital as the 1s orbital associated with hydrogen. A coarse approximation, and we'll now think about in the next, in this lecture and beyond, about going, getting improvements on that description. So one of the things that we reminded ourselves about last time was that even though we're thinking about these as independent particles and in zeroth order and not thinking about coupling between them, we have to deal with the fundamental problem of identical particles because the two wave functions can overlap and therefore they become indistinguishable, and in that case we need to be very careful about properly symmetrizing the overall state. In fact, as we know, the overall state has to be antisymmetric under exchange, which means that we have a pairing here in which we paired either symmetric or antisymmetric couplings of the orbitals with the corresponding antisymmetric or symmetric couplings of the spins. Right? So for example, if we're talking about the ground state where both of these orbitals are the same, then by the Pauli exclusion principle, the only way we can have that is if the spins are in the singlet state. So there's only one possible state in that case. So with this ansatz, we found an expression for what the energy is associated with this bound state. And it involves the zeroth order hydrogenic-like energies, and then terms having to do with the interactions between the electrons. And that involves a term that in the jargon here is we call J, and a term we call K. The term J is what you might have just written down from the point of view of thinking about this from a classical like picture. If I think about each electron as a kind of charge density with a probability density associated with its orbital, then I have this Coulomb, this would be the electrostatic Coulomb energy associated with two charge densities. One charge density given here and another charge density here. And that would be the electrostatic potential energy. And that gives a repulsive energy and reduces the binding by the amount J. But there's another term here which comes from the fact that we have the anti-symmetrization of the overall state, and that is a term that has no classical analog. It's the exchange interaction, and it can either increase or decrease the total interaction energy. That is to say, there is a kind of effective interaction which is sometimes called the exchange interaction, which is if I have two electrons, say, in the same spin state, then there is a kind of effective repulsion between them. They can't get close to one another because of the Pauli exclusion principle, which means that there's a reduction in the amount of repulsion that they see, because they just don't get very close to one another. On the other hand, if they're paired together in a spin triplet, so that is to say, symmetric under exchange of the spins, then let's see, it's the other way around. Yeah, I'm sorry. I just got myself confused. Let me say this again. So when they're in the same spin state, that's an example of one of the triplets, right? That's a symmetric under exchange. And that in that case, they have the Pauli exclusion principle says they can't be in the same position. On the other hand, if they're paired in a singlet, antisymmetric under spin exchange, then there's an enhancement of their probability to be at the same place. There's an enhancement due to the exchange density, and that means that there is additional repulsion. So what that gives us, this picture is not to scale, is if I thought about one of the excited states of helium, as we discussed last lecture, and as we discussed last lecture, the only excited states are the ones where one of the orbitals is like a 1s orbital, and there's only one optically excited electron. Because if we had two optically excited electrons, we said that was already above the ionization potential, where one is bound and the other is free. So all of the excited states of helium have this kind of configuration. And we end up with a pairing of either singlet or triplet. Okay. So I introduced here what is called term notation. That is to say, when we specify the energy level of our multi-electron atom, we specify typically two things. One is what is the configuration of the electrons in terms of the this picture of independent orbitals, and we'll get beyond that, because that picture, this was a kind of a coarse approximation. Is this always what we do? And the answer is yes, for reasons that we'll explain. They will go beyond this hydrogenic picture, but we always think about a configuration of the independent electron orbitals, and then a kind of coupling. And one way that we couple them is to say there's a total angular momentum. I'm going to say the total orbital angular momentum. And we typically write that with a capital letter. And then the multiplicity, whether we're talking about triplets or singlets or beyond, is written in terms of the superscript on the left. So this is the singlet, and this is the triplet. That's what that means. And then if we include, in addition, as we will at some point, the spin-orbit interaction, and if the spin-orbit interaction is such that it's a weak interaction, so that first we couple the orbit together, and we couple the spin together, and then we couple the orbit to the spin, as opposed to couple orbit to spin independently for each electron. That would be, in some sense, a better approximation if the spin-orbit coupling were very large. But in this approximation, which is sometimes called the Russell-Saunders coupling, then we would put, in addition, the J quantum number as the subscript to the right. So this is a kind of notation that you will see when one is talking about the energy levels in atoms. If we had only a one electron atom, then we could still use this kind of notation. For example, you will see that at times. You will see, you know, the multiplicity here being 2, having to do with just 1 electron, right? In this case, you know, for example, if I had, if I'm thinking about an alkali and I just have 1 electron that I care about, then I will talk about something like the 2p3 state. So again, there's 2 kinds of notations. There's the orbital associated with the individual electrons, and then there's some quantum numbers having to do with the total angular momentum of the system. All right, so let's see, where did our erasers go? Let me grab one back here. So let's see. I wanted to just sketch again the. Let me get it over here. I wanted to sketch again the energy spectrum, just so we can take a look at it together. And it's probably easiest if I just got the picture correct. So here it is. Okay, let me draw it for you. So the spectrum of helium. That is the case is equals to looks like this. If I take the 0 of energy as the case where I have doubly ionized and 2 electrons, then the ground state is down here at 78.8 eV. So this is all in electron volts. And then the minus 54.4 is the case where I have hydrogenic ground state with an alpha nucleus and 1 electron. So this is just the case of ionizing 1 of the electrons. And then I have this is the ground state. And then I have the excited states. And they separate into the triplets and the singlets. Okay? So up here, what we have are also, we have the doubly excited autoionizing states. And we also have states in which I have excitations. So this is all the continuum here. I can have, for example, an excited helium ion plus a single electron. That's up here as well. So those are all the states associated. And of course, up here is all the continuum of the double electron. Yes, Cornelius.
Just a question on the notation.
Uh-huh.
Last time I think you always wrote 1s in parentheses and then 2.
So let me.
What does this mean?
This notation here. This is the term. So this is n. This is the.
Yeah.
This is the multiple. So I haven't written here the configuration. This is all 1s squared.
Okay.
Okay.
Yeah.
In this case, I have 1s, 2s. So if I use a small lowercase letter, that corresponds to the orbital of the individual electron. The capital letter, the uppercase letter, represents the total angular momentum. So let's look at this a little bit more carefully. Let's look at the bound states of helium, where both electrons are bound. And let me copy this picture of this book. So now I'm going to just look at this, the bound states. Two electrons in helium. And the spectrum looks like this. So now I'm going to take the zero of energy here. And the ground state here, so let's see. We got -1, -2, -3, -4, -5, and then way down here is -25 electron volts. So the ground state is here at 24.6. That's the, and then over at about 4 eV, I have, let me write it, 2 1s, and then this guy is up here. This is 3 1s, and then up here I have the 4 1s. Then I have the 4 1p. I have 3 1p. I have the 2 1p. These are all the the singlets. And then I have the triplets. The triplets, let's see, this is down at just about 5. 2 triplet S. I got the 2 triplet P. Triplet S and the 4 triplet S, and I got down here the 3 triplet P, etc. And then there are these states for each of these. So let me explain what this picture is telling us. Again, we have this 2 kinds of states because the electrons can be paired together as triplet or singlet. The ground state must be a singlet. There's no possibility of something nearby being a triplet. In fact, we see there's a huge energy difference here. This is the excited state. The triplets are supposed to always be lower in energy than the singlets, for the reason that we described. The singlets have more repulsion. And there's a big energy difference, in terms of the triplets versus the singlets. This is something that is way optically resolvable. And each one of these corresponds to a particular configuration. These are all of these have one of the electrons in the 1s orbital, and then the other electron is in an excited orbital. In this case, it's excited in the 2s, the 3s, or the 4s. And this is excited in the 2p, 3p, or 4p states. Okay. Now, as we'll discuss in a few weeks, when we talk about the interactions of atoms with electromagnetic fields, and as an example of that, the problem of decay or spontaneous emission, there are selection rules which tell us which transitions are allowed and which transitions are forbidden and which transitions are strictly forbidden. The transition between triplet and singlet are not allowed. Yeah?
So this restriction on the excited states that one has to always be in the 1s ground state means that for these highly excited state, the exchange interaction becomes less and less important. I'm assuming because the wave functions have less and less overlap. Is that, you know, it's kind of a restriction on K, because one of the electrons is always in the ground state spatial wave function.
That is correct in these two electron atoms. I mean, if I had more in the subshell, I'd have to think about that more carefully. But that surely seems correct. And if I look at the the picture, which I'll scan in and put in the notes, it certainly does appear to be the case. So that I think that's correct intuition. The point I was about to make is that spontaneous transitions between triplet and singlet is forbidden. Which is why in the olden days, probably in the 19th century and early 20th century, there was thought to be two independent chemical species of helium, orthohelium and perihelium, because they had independent spectral lines. They were the same, clearly they were the same element from other kinds of experiments that could be done, but in terms of the spectral lines, there was spectral lines associated with one thing that was called orthohelium, and the other one was called para. I forget which one is which. Does anyone remember? I think the ortho is the singlet and the para is the triplet. There are these quantum numbers that I've written down are not perfect. I've done, first of all, a very coarse approximation. We'll talk about getting a little bit better, but this idea that I have independent orbitals and then singlet and triplet couplings of those independent orbitals is an approximation. So these quantum numbers are pretty good quantum numbers, but they're not perfect quantum numbers. So when we talk about the triplet S state, it actually has a tiny bit of singlet in it. It's not pure triplet or pure singlet. So there can be some decay. Well, that one would be pretty darn impossible, but this one. And this is what's called an intercombination line. This state has a very long lifetime and doesn't decay very often because it doesn't have very much singlet character in it, but it has a tiny bit. And so those are very narrow lines. They're used in astronomy. It's also the basis of modern clock technology because I have you know about atomic clocks, that the basis of the second is based on the transition. Currently, it's based on the hyperfine transition in cesium, in the ground state of cesium. But that's a microwave transition, and that has a limit. It'd be much better if we could have a much higher frequency line defining the unit of second. And in current research, the transition on this kind of intercombination line between a triplet P and a singlet S is the basis of the so-called optical atomic clock. And it's very sure soon to be redefined to be the second. I don't know if it's going to be strontium or calcium or one of the other group 2 elements or ytterbium, which kind of looks like that. But that's on the agenda. Yes?
Yeah, but didn't you say it's forbidden? Or?
It's not exactly forbidden.
So
it's forbidden. We'll talk about this in more detail. When we write down, the point I wanted to try to make here is that these quantum numbers are not perfectly good quantum numbers.
Okay.
They're approximately good quantum numbers. In the same way as we just saw in the homework that you handed in, when we look, for example, at the Zeeman effect in the ground state manifold of hydrogen, when the magnetic field was weak compared to the hyperfine splitting, the m sub f's were approximately good quantum numbers. They're not exactly the right good quantum numbers because it doesn't really commute with the total angular momentum does not, F and m sub f doesn't commute with the Zeeman interaction. But when the Zeeman interaction is tiny compared to the hyperfine interaction, then we kind of keep those quantum numbers around. The same thing is true here. When one writes down triplet P as, one should take that, understand that it's not actually exactly a triplet state. That came from the fact that we assumed something about the nature of those orbitals. Okay? So as, for example, it turns out the hyperfine interaction mixes a little bit of triplet with a little bit of singlet and makes this transition then allowed. If it was truly pure triplet, then this would be forbidden.
What's the lifetime of this thing?
Well, it depends on actually the case of the fine structure. So in this case, let's just quickly think about that. What are the so here, in my spectroscopic notation, I wrote down that there's the multiplicity, the L, and then there's the J. So what are the possible J quantum numbers for this triplet P state? Well, J is the sum of L and S. And according to the rules of addition of angular momentum, J can be between the sum of L plus S eigenvalues and the magnitude of the difference. So what are the possible values here of J? Well, in this case, L is 1, and S is, there's 2 electrons, they're paired in a triplet, S is 1. Okay, it's a triplet, it means S is 1, meaning the total S. So total S1 added to total L1, can you give me a J equals 2? A J equals 1, and a J equals 0. Okay, so there are 3 states. Now there's also hyperfine, depending on the nuclear spin, but some of the species don't have nuclear spins, so there's just fine structure. It's not split exactly like that, but anyway. So this is a singlet S. So what is J in this case? What is L in this case? 0. What is the total spin? 0. I know, it's so confusing. It's a singlet. Singlet means as a 0. Now that one, I don't know who made up this notation, but they did. Okay. So what's possible J in this case? 0. So to answer Rob's question, we need to remember, or have learned sometime, or we'll wait a few lectures, and remember the selection rules of J. So there's also a transition that J can change by a certain case. In this case, delta J equals 1 is allowed. So of all of these, this is the strongest line. These 2 lines are not allowed in a dipole transition. In fact, this guy is really, really, really forbidden. The triplet P0, because to go from J equals 0 to J equals 0, there's just no way to do that because the photon has some angular momentum. So how the heck is it going to do that? It's not going to conserve angular momentum. So this is actually the transition that's being, originally this one was, and that line width is on the order of kilohertz, depending on the species. Whereas this line has a line width on the order of millihertz. So that's a factor of 1,000,000 less than this, and a factor of you know, a billion less than the strong transition on that. There are quadrupole transitions as well. This is not. This is a dipole transition.
I mean the other.
This guy.
0.
Yes, that's a quadrupole transition. No, the 0 to 0, that's completely forbidden. Even quadrupole, because you can't add 0 to quadrupole and get 0. It's just impossible. You can't go from 0 to 0 adding anything. This is only allowed at all because there's some mixing in, because this is not the perfect quantum numbers. So in fact, in optical clocks, one of the questions is how do you make this allowed? If you have nuclear spin, then the hyperfine interaction actually mixes a little bit of the singlet with the triplet. But then you have problems of the nuclear spin and what that does to the clock. There are other things that people have done by adding magnetic fields to try to mix these levels together and make this an allowed transition, or at least, you know, have a little piece of it that's allowed. So yeah, it's a question. So you know, that's what the research is about. All right. All right. Let's now get a little bit more quantitative about this. And let's look at the ground state in particular to start. So, in the ground state, we don't have the exchange interaction. And this then is equal to minus 2 z squared. No, sorry, it's just minus z squared plus over R12. So this was our hydrogenic contribution for the 2 electrons, right? Twice z squared over 2. And this can be calculated, and what you get is oh gosh. So that's what we get from this perturbation theory calculation, treating the interaction of the electrons with one another as a perturbation. Okay. And for helium, this gives this energy is minus 0.5 atomic units. Okay, and the exact result from experiment is minus 2.904. So it's not terrible. If I look at another 2 electron atom, if I look at carbon 4 times ionized, okay, that's a 2 electron atom. Carbon has 6 electrons. What you find is that in this case, the energy of this is minus 32.5 atomic units, and the exact is minus 32.41. So it gets better. It gets better when Z is bigger because the electrons are more tightly bind to the nucleus, and the effect of the repulsion from one another is small comparatively. They don't see each other as much as they see the nucleus. So this gives us a little bit of a hint that really, I mean, part of the problem here is that we did a very coarse approximation and treated each electron independently, ignored their interaction, ignored their repulsion, calculated just hydrogenic orbitals for each of those, and then calculated the perturbation energy in that hydrogenic orbital. Whereas, in fact, we have if we think about it for just a little bit, in some sense, we're not taking into account the fact that one of the electrons screens the nucleus, screens the Coulomb attraction of the nucleus, as seen by the other electron. So that the binding that one of the electrons is feeling is not really the binding to a bare, in this case Z equals 2 nucleus, but the binding that is screened in some way by the other electron. Now, what we want to do, and we're going to, I mean, to really do this properly, to really study atomic structure in a very formal, rigorous, and proper way, we'll spend the rest of the semester just doing that, or at least a few weeks just doing that. And that's not what we're going to do. We're just going to get a little bit of a feeling and gain a little bit of intuition about that, and then we're just going to use atomic structure to think about the manipulation of atoms. But just to get a little bit, make a little bit of progress on that, and spend the next few lectures on it, let's think about how we can make our solution just a little bit more sophisticated. So we want to take into account the screening of the nucleus by electrons. So there's many different approaches we can take. One approach we can take right away to take this into account is to turn to the variational approximation. Now, I'm not sure if this is something you've seen in your quantum mechanics classes before, but let me review it quickly. The point is the following. We want to, for example, let's say we seek the ground state. But it can be extended beyond the ground state, but for the moment, let's concentrate on the ground state. Okay? Now, we don't know what the ground state wave function is. But based on our physical intuition, we can parameterize the wave function in some way. Okay? So for example, so we want to use physical intuition to parameterize the wave function or the state. So, for example, right now we've taken as our 0th order wave functions the hydrogenic orbitals associated with z equals 2. That's what we did at this stage. But what we could think about is, instead of having the nucleus be z equals 2, we say it's a screen nucleus with some effective atomic number, effective charge, z effective times e. We don't know what that is, but we are going to say that what the electrons see is effectively something that looks like the averaging of the, this electron, here's the nucleus, and the other electron is sitting here screening it, and this electron sees a z effective. So, for example, we could say that the orbitals here now is a new kind of 1s squared, where these phi 1s's, let me write this down. Oh, there's my notes. Are hydrogenic 1s orbitals, but with some unknown screening. If we ignored screening, which is what we did over there, this is 2. And then the goal is to find z effective that best approximates the ground state. So how do we do that? Well, that's what the variational approximation is about. The variational approximation says, let us parameterize through physical intuition the eigenstate, in this case the ground state, in some way. So generically, what we say is that the energy is some function of some set of parameters. I'll call them lambda. We parameterize in some way the wave function and calculate this wave function is supposed to be near the ground state. Now, generally speaking, when one does this, one often doesn't choose the parameterization, may make it complicated to normalize. So at the end of the day, make sure that you normalize it. It might be just too messy to include that normalization in the parameterization. In this case, we did because it was easy. But in many cases, like the first problem for homework, it's not so easy. So at the end, you have to normalize it. And the claim is that this energy is always bigger than or equal to the ground state energy. Well, that's pretty easy to see. Because if I expand this in a complete basis, right. Of energy eigenstates, whatever those are. I'm just saying they're labeled by n. This is E sub n, because this is an eigenstate. Okay, so I'm taking n to be the actual eigenstates of the Hamiltonian. Then, if I subtract out let's call n equals 0 the ground state case, then this becomes En minus E0 times plus 0. So, since these energies are all positive or equal to 0, well, in the case of this, if I chose my wave function to actually be the ground state, then this term would be 0. But in general, it will have some overlap with all of the other states. And since these energies are all positive, this energy is greater than E0, the component of the ground state. So, the moral of the story here is that whatever parameterization I use, if I calculate the expectation value of the Hamiltonian, that expectation value will always be bigger than the true ground state of the system. Always. And therefore, if I can calculate this expectation value, and then just minimize this function, well, then I find some approximation to the ground state. And I can just keep trying different parameterizations and try to see if I can get them smaller and smaller and smaller and smaller. This is not a controlled approximation in the same way that perturbation theory is a controlled approximation, where we have a convergent power series and we can think about higher order corrections. This is the art of physics. The art of physics is the art of approximations, using your physical intuition to paint the best picture you can. So we can see, whether we do better by doing this, because we can see whether it's smaller than what we had with our rough approximation based on z equals 2. Let's see what we get. So this is going to be our parameterization. We have one parameter, the z effective. And our goal here now is to calculate the expectation value of the Hamiltonian and minimize that expectation value with respect to this parameter, find what that parameter is, and then find what this approximation gives us to the energy. Okay? So, let's find the energy, the expectation value of the Hamiltonian with respect to this new variational guess to the shape of the wave function. I chose it normalized, so that's fine. Okay, so what is this? This is going to be equal to the sum the Hamiltonian is still the same Hamiltonian. I'm not parameterizing the Hamiltonian. I'm parameterizing what the ground state wave function is. Let's put this in atomic units. So what is this? Let me call, so psi tilde 1s squared is going to be phi tilde r1, phi s 1s tilde r2. The spin doesn't play a role here. Okay? And these is what I just erased. So what is this going to be? This is going to be equal to twice the expectation value of p squared over 2m this is attraction, not repulsion, excuse me, minus z one over r. So that's the terms that don't have to do with the coupling between the electron, and then I have plus the repulsive energy associated with this waveform. Okay? So we have to calculate these things, and we can do that by eye. Because, what do we know? These are hydrogenic wave functions, but with a different effective z, right? So we know that these wave functions generally are going to be equal to p squared over 2 minus z effective times 1 over r acting on this is equal to minus 1/2 n squared is 1 in atomic units. Times z effective squared. Right? That's what the wave functions were chosen to be. They were chosen to be the eigenfunctions of a hydrogenic Hamiltonian with this nucleus. And we know that the eigenvalues are minus 1/2 the principal quantum number squared times the effective squared. But we don't have z effective. Here we have z. So what are we going to do? Well, what we can turn to is what everyone remembers, the Vireo theorem. Remember the Vireo theorem? Maybe. Heard of it. Forgot it, what exactly it is. Maybe.
It's also true for if you have several electrons there.
We will talk about that. How this approximation, that's something we'll hopefully begin to explore at the end of the day. Today and into Monday. But the Vireo theorem tells us a relationship between the average kinetic energy and the average potential energy. So the Vireo theorem tells us for a 1 over r potential, the average of p squared over 2m is equal to minus 1/2 the average of the potential energy. So that means, since the total energy is equal to the sum of the two, that the average of p squared over 2m is equal to minus twice, in a particular principal quantum number, minus twice the binding energy, and the average potential energy is equal to Right is equal to 12 standards per second. Yeah. Okay, so with that said, we can calculate these things. The average is equal to minus 2 times that. That's equal to Z effective squared. And then we have Z times the potential energy is equal to, so I have to divide by Z effective, multiply by Z effective, this energy then is Z effective squared as well. Or Z times Z effective.
Yes. Mr. Deutsch.
Yes, sir.
Is the 2 that you wrote, the upper one of the 2, is that correct? We wrote average kinetic energy is minus 2 EM. I think it's just minus EM.
Minus EM.
I mean, else they would add up to
yeah,
0.
indeed, that is true. That is true. That is true. Missing a factor of 2 here.
No, the upper one, I think.
The upper one is, you're right, thank you. Double check something. Yes, that's correct. Sorry. That's correct. Okay, but these still are correct. And what that tells us now, finally, we can calculate what this is. We did that, or at least I wrote down what the solution to this was in the context when we had the hydrogenic with Z, and we said that that was equal to 3/8 Z, in this case 3/8 the effective, if we do that integral. So putting all of that together, what we find is that the average Hamiltonian in this case is given by the following. Z squared minus twice this thing, Z effective times Z, plus 5/8 effective. So this was the average kinetic energy, twice the average kinetic energy. This was twice the average potential energy. And this was equal to the average of the propulsion. So now we can just look at this function, and this function is convex. It has a minimum. Minimizing this, we find that the effective Z is equal to Z minus 5/16. So, given that, according to this approximation, the energy of the ground state of helium is equal to minus the effective squared. That's equal to minus Z minus 5/16 squared. And for Z equals 2, that is for helium, this is minus 2.848, which is pretty good. It was a 2.904 in atomic units. We had was the exact binding energy. So by doing this variational approximation and using our physical intuition, we got pretty close already to the exact ground state energy of helium.
Yeah, sorry, what was the energy before? It was -2.7?
Yeah, I don't know, I have to look at it. You mean with that, if it was just, if we just had the repulsion energy?
Yeah.
I don't remember, Rob.
All right, well, my real question actually is,
Yeah.
I would figure that if you're screening out part of the nuclear charge,
Yeah.
the outer electron would see less attraction, so that would raise the energy, so it wouldn't get less, more negative.
No, it's a question of how much the repulsive energy is balanced by the attractive energy. So it's a question of where the electrons are relative to one another. And what we showed here is that no matter what we do, our variational calculation will have to lower the energy. Now, there isn't a point related to this that you're raising, which is as I said, this is an art. Is thinking about this physically, if I were to think about what the effective potential is seen by one of the electrons due to the other, what might I think? Well, one way to write this down is to say if the electron is very close to the nucleus, it's dominantly seeing the effect of the nucleus, in which case I would see something like, that looks like -2/r. Whereas if the electron is very far from the nucleus, the other electron is completely screening it out, in which case I would see something that goes like -1/r. So I shouldn't see a pure Z effective over R potential. I might expect something which asymptotically approaches a 1/r and then somehow for short distances becomes a -2/r potential. And intermediately, it's something else. It's not a 1/r. And this is what's known as the central field approximation. This potential is not some Z effective times 1/r. It has a different asymptotic behavior intermediately. And we could try to then parameterize. You could say the effective potential is you know, something which for small distances maps to this, and for large distances maps to that. This is will allow us to make a more systematic approximation, and we'll pick that up in the next lecture, but let me just foreshadow a little bit and tell you where we're headed. What we had here was the Hamiltonian that we had was a sum over all the electrons. In general, in this case, there are two. But as was pointed out, what happens when we have more than one? I can say, well, there's some plus the sum I not equal to j, 1 over Rij. This is our electrostatic Hamiltonian. What we want to do is write this in some way as in other words, we'd like to somehow take some of the effects of the other electrons and put that into some effective potential so that each electron sees some effective potential, where this effective potential is equal to the attractive interaction of the nucleus plus some screening potential, which is taken to be somehow spherically symmetric. The degree to which this is a small term compared to this means that we can treat this as independent electrons, each in their own independent orbital, ultimately properly symmetrized according to the Fermi statistics that we need to have. But of course, the effective potential depends on all of the other electrons. So this is what's known as we'll see in detail, the mean field approximation. More familiar in modern condensed matter physics, but it really was born in treating the structures of atoms, because many electrons is many bodies. So we're going to write down an ansatz, an assumed form in which each electron is, so that we kind of have a product wave function, but then self-consistently solve that in the best way possible so that one electron sees the potential averaged in some way due to all the others. And that's what this picture is attempting to capture. One of the upshots, if this approximation is a good approximation, is that, well, to the degree to which we ignore this, then what we have is spherically symmetric potential, but not a 1 over r potential. In which case, we still have good quantum numbers. And L m sub L. And that's why the configuration that we wrote down of the electrons in, say, helium or in higher atomic number atoms are always still written, like in your chemistry periodic table, as filling up orbitals. Those orbitals are not hydrogenic orbitals. They're Hartree-Fock orbitals. They're the orbitals associated with the mean field theory, which gives us, to the degree that it's a good approximation, spherically symmetric effective potentials where that spherically symmetric potential is not a pure 1 over r potential, but something related to the combination of the nucleus and the screening of all the electrons. And how we do that self-consistently is what we're going to discuss next week. All right? So, we'll leave it there for now. I have your homework here. Please hand in your assignment. We can get started on the next assignment. You have what you need. All right? You could have gotten started in the first week. And no one came to the problem session last week. I was there. So I will be cognizant about trying to make sure that if it's a 2-week assignment that you can get started on that work in the first week. So you don't, I agree, if you tried to do it all in the last week or in the last few days, it would have been a challenge. The current assignment, you should be able to do it starting this afternoon. And you have 2 weeks. So I think it's a reasonable amount of work for the graduate course here. But we'll try to pay attention. And if we're finding that the assignment is, you don't have the material you need to get moving on it once the assignment started, then I will certainly be happy to give an extension. So I'll be aware of that and just let me know. Okay? All right. So let's see. We were talking about last time, looking at now an atom with more than 1 electron, in particular an atom with exactly 2 electrons. So the generic problem here involves some 2 electrons and a nucleus. And if we ignore any of the effects associated with magnetic effects and associated relativistic corrections, and we getting improvements on that description. So one of the things that we reminded ourselves about last time was that even though we're thinking about these as independent particles and in 0th order and not thinking about the coupling between them, we have to deal with the fundamental problem of identical particles because the 2 wave functions can overlap and therefore they become indistinguishable, and in that case we need to be very careful about properly symmetrizing the overall state. In fact, as we know, the overall state has to be antisymmetric under exchange, which means that we have a pairing here in which we paired either symmetric or antisymmetric couplings of the orbitals with the corresponding antisymmetric or symmetric couplings of the spins. Right? So for example, if we're talking about the ground state where both of these orbitals are the same, then by the Pauli exclusion principle, the only way we can have that is if the spins are in the singlet state. So there's only one possible state in that case. So with this ansatz, we found an expression for what the energy is associated with this bound state. And it involves the 0th order hydrogenic concentrate to lowest order on the electrostatic interactions. Then this is our Hamiltonian. It's a very simple Hamiltonian associated with the attraction of the 2 electrons to the nucleus and the repulsion between the 2 electrons. So we can think about this as each term associated with the independent attraction of each electron independently to the nucleus is a hydrogenic-like Hamiltonian. And then we have the correlation effects having to do with the interactions between the electrons. So a coarse approximation that gets us started here is to look at the problem from the point of view of perturbation theory, whereby we treat this as a perturbation and think about this as our zeroth order Hamiltonian. And so our zeroth order wave functions then are the wave functions associated with two electrons, one in one of the orbitals associated with that hydrogenic atom and another with a potentially same or different orbital. So for example, the ground state here would be both both electrons in a 1s orbital. And in this case, we're thinking about that 1s orbital as the 1s orbital associated with hydrogen. A coarse approximation, and we'll now think about in this lecture and beyond, about going. I have graded assignments here. We'll pick them up at the end of class. The current assignment, problem set 2, is due today. On the web now are all of the current lecture notes up to yesterday's or Monday's lecture, and all of the video are compressed and ready for viewing now. Thanks to Ben and Rob. And the next problem set is posted, and it's a 2-week assignment as well. But don't wait. Get started.
Yeah.
Yes.
I'd like to say something on the one for this week.
Uh-huh.
I think we all have problems to finish it in time. Well, it was very much, but I don't think I can say something against that. But we should have more time, because most of the things we needed for it, we did in class on Monday. And the problem session is also on Monday. Actually, we did almost everything on the last 2 days, less than 2 days. I think it's better if we had more time for that.
All right, well, we'll try to beware of, there was 2 weeks to do that. What we did on Monday was the hyperfine structure. There was only, the last problem required you to know that. The rest of that was just angular momentum addition. And if you had gotten started and had questions about the first week, I certainly could have answered that. So there were 2 weeks in that assignment, and I think there was quite a bit energies. And then in terms having to do with the interactions between electrons. And that involves a term that in the jargon here is we call J, and a term we call K. The term J is what you might have just written down from the point of view of thinking about this from a classical-like picture. If I think about each electron as a kind of charge density with a probability density associated with its orbital, then I have this Coulomb, this would be the electrostatic Coulomb energy associated with 2 charge densities. One charge density given here and another charge density here. And that would be the electrostatic potential energy. And that gives a repulsive energy and reduces the binding by the amount J. But there's another term here which comes from the fact that we have the anti-symmetrization of the overall state. And that is a term that has no classical analog. It's the exchange interaction. And it can either increase or decrease the total interaction energy. That is to say, there is a kind of effective interaction which is sometimes called the exchange interaction, which is if I have two electrons, say, in the same spin state, then there is a kind of effective repulsion.